Welcome to our exploration of integral calculus. Today, we are mastering the washer method, a powerful technique for finding the volume of a solid of revolution when there is a hollow center. Think of it as finding the volume of a large solid and subtracting a smaller solid from its core. This method is essential for engineering and physics applications. Before we dive in, remember the disk method. When a function's area is flush against the axis of rotation, each cross-section is a solid circle with area pi times the radius squared. The washer method is simply an extension of this principle, designed to account for a variable in a radius that creates a void. Let's look at the geometry of a single cross-section. A washer is just a large circle with a smaller circle removed from the middle. The area of the large circle is pi times the outer radius squared, and the area of the hole is pi times the inner radius squared. Subtracting the two gives us the area of the washer's face. To set up our integral, we first identify our boundaries. We typically have an upper function and a lower function. When rotating around a horizontal axis like the x-axis, the function further from the axis becomes our outer radius, while the function closer to the axis becomes our inner radius. This leads us to the formal washer method formula. The volume V is equal to pi times the integral from a to b of the outer radius squared minus the inner radius squared. It is crucial to square the radii individually before subtracting them. Subtracting the radii first and then squaring will result in an incorrect answer. Think of the integral as an infinite sum of these thin washers. By adding up the volumes of infinitely many slices with thickness dx, we arrive at the exact volume of the solid. This is the beauty of calculus, turning a series of discrete approximations into a single, precise calculation. Now we plug these into our formula. Our integral goes from 0 to 1. We square the outer radius, square root of x, to get x. Then we square the inner radius, x squared, to get x to the fourth power. The expression inside our integral is now simplified and ready for evaluation. We find the antiderivative of x minus x to the fourth, which is x squared over 2 minus x to the fifth over 5. Evaluating this from 0 to 1, we subtract 0 from the value at 1. This leaves us with 1/2 minus 1/5, multiplied by pi. The final calculation gives us a volume of 3 pi over 10 cubic units. Visually, this solid looks like a shallow bowl with a curved interior. By using the washer method, we successfully accounted for the empty space in the middle that the disk method would have ignored. What if we rotate around the y-axis? Let's take the region between y equals x squared and y equals 2x. To integrate with respect to y, we must solve for x. The curves become x equals the square root of y and x equals y over 2. The limits of integration now follow the y-axis. The intersection points are at y equals 0 and y equals 4. The outer radius is the function furthest to the right, which is the square root of y. The inner radius is y over 2. We set up the integral as pi times the integral from 0 to 4 of y minus y squared over 4. Integrating gives us y squared over 2 minus y cubed over 12. Plugging in 4, we get 8 minus 16 thirds. When we simplify 8 to 24 thirds and subtract 16 thirds, we are left with 8 thirds pi. This is the volume of our vertical revolution. Advanced cases involve rotating around lines other than the axis. If we rotate around y equals -1, the distance from the axis changes. The radius is no longer just the function value, it is the function value minus the axis value. This shifts our radii calculations. Always remember, the radius is the distance from the curve to the axis of rotation. If the axis is y equals k, the radius is the absolute difference between the function and k. This ensures that even when the solid is shifted in space, we accurately capture the dimensions of each washer. If the axis of rotation is above the region, say at y equals 5, then the function lower down actually creates the outer radius because it is further away from the axis. The function closer to the axis always creates the inner radius, regardless of which one has a higher y value. Sometimes functions cross within the interval. In these cases, the outer and inner function swap roles. To find the total volume, you must split the integral at the intersection point and set up two separate washer calculations, then sum the results to get the total volume. The most common mistake is squaring the difference of the radii. Remember, the area of a washer is the difference of two areas. Mathematically, r squared minus r squared is not the same as the quantity r minus r squared. Always square each radius individually before subtracting them in your integral. Another frequent error is using the wrong differential. If you are rotating around a vertical line, you must use dy. This requires you to rewrite your equation so x is a function of y. Using dx for a vertical rotation is a recipe for an incorrect setup. It sounds simple, but many students forget to include pi in their final answer. Since we are summing circular cross-sections, pi is a constant multiplier for the entire volume. Always write it outside the integral at the start so you don't lose it during the calculation. To summarize, the washer method calculates the volume of hollow solids of revolution. Start by sketching the region and identifying the outer and inner radii relative to the axis of rotation. Set up your integral using the squared radii, include pi, and evaluate between your boundaries. Quick question: if the region is bounded by y equals x and the x-axis, is this a washer? No, because the region is flush against the axis, the inner radius is 0, making it a simple disk. The washer method is just a disk method where the whole matters. Thank you for learning with us. Generated by Vision Solve AI.